Okay, this is now your sample problem number 3. Using the dot product, find the components of the force F equal to 2I plus J in kilonewtons in the direction of the x prime axis and that of the y prime axis. So we were given a force F, which is, so this is now your vector F, and this is equal to 2I plus J. So what is therefore the component of this vector in the direction of x prime? So let's try to determine now the component of the force F in the direction of x prime is now equal to that vector, that a unit vector in the x prime. So that is in the desired direction. So we have a unit vector. So I'm just going to have the orthogonal unit vectors in the x prime. So this is your x prime. So let's try to determine now a unit vector in the direction of x prime. So we have a unit vector in the direction of x prime. So first, let's try to determine now the component, of this unit vector u prime x. So the magnitude of the component, so we now have magnitude. The magnitude of the component of the unit vector x prime is your ux prime is now equal to, since this is a unit vector, then the magnitude is equal to 1. So we have 1. The unit vector in the direction of x is now equal to 1. 1 is the magnitude of a unit vector, and that one is cosine of 60 degrees. And this one in here is now equal to, so this is therefore equal to 0.5. So 0.5. And the component of the unit vector in the direction of y. So in the direction of y is now equal to, so this is therefore equal to 1. Multiply this one by sine of 60 degrees, and this one is now equal to 0.866. So 0.866. Hence, the unit vector in the direction of x prime can be expressed as 0.5i plus 0.866j. Let's now determine the component of the vector f, which is equal to 2i plus j in the direction of x prime. So your fx prime is therefore equal to, we have 2i plus 2i plus j. 2i plus j dot a unit vector in the direction of x prime, and this is equal to 0.5i plus 0.866j. So evaluating the dot product of the two vectors, we now have equal to. So we have now your 2i. So this is 2 multiply this one by 0.5. So that is 2 times 0.5. Plus we now have 1 multiply this one by 0.866. So this is therefore equal to 1 plus 0.866. And therefore, the component of the vector f in the direction of x prime is equal to 1.866 kilonewton. Now, what is also the component of the vector f in the direction of y prime? So in the direction of y prime, the component of the vector f in the direction of y prime is still equal to the vector f dot a unit vector in the direction of y prime. So if this is now the unit vector in the direction of y prime, so we have the unit vector in the direction of y prime. So the component, again, let us try to get now the magnitude. So we have the magnitude of the components of the unit vector in the direction of y prime. So again, the component in the x-axis, the magnitude of the component in the x-axis is now equal to 1. The magnitude of a unit vector is equal to 1. Multiply this one by cosine of 30 degrees. So since that is now going to the left, so we have negative 1. We have cosine of 30 degrees, or this is equal to negative 0.866. So negative 0.866. And the component of this unit vector in the direction of y is now equal to, okay, so it's going up, so we have positive 1. We now have sine of 30 degrees, or that is equal to 0.5. Hence, the unit vector y prime is now equal to minus 0.866i plus 0.5j. Hence, the component of the vector f in the direction of y prime is now again equal to that vector, which is equal to 2i plus j dot a unit vector in the direction of y prime. So negative 0.866i plus 0.5j. So this is equal to 2. Multiply this one by negative 0.866. Okay, so we have plus, okay, 1, multiply this one by 0.5. So this is therefore equal to negative 1.732 plus 0.5. And this is therefore equal to negative 1.232 kilonewtons. Again, the negative sign here indicates that the component of this vector in the direction of y prime is in the opposite sense of this unit vector y prime. We have sample problem number 4. Now, in the system shown, a force F acts from B to D. So, this is now the vector F which is acting from B to D. So we have the vector F is acting from B to D. So this is now your vector F of acting from B to D. Find the magnitude of this vector F if the components along the boom A, B, C is 850 pounds. So this is 850 pounds. So we now have the component of this vector along boom A, B, C is equal to 800 pounds. So that is equal to 800 pounds. So we noted before that the component of any vector in any desired direction is equal to the dot product of that vector and a unit vector in the desired direction. So first, let's try to determine now. Let us try, since we are required to determine the component of vector F. So this is your vector F in this direction. So what is therefore the component of that vector F in the direction of A, B, C? So we now have the component of this vector A in the direction of ABC is now equal to the vector itself dot a unit vector. Okay, dot a unit vector. So I'm just going to consider BC. Point BC is along ABC. So that a unit vector VC. And this is now your position vector. So first, let us try to introduce a position vector from B to C. Let's try to introduce a position vector from B to C. But before, let's try to determine the coordinates of the different points. So we have now the coordinates of points. So we now have your A. So the coordinate of A, so your x coordinate of point A is, coordinate of point A is equal to 12 in the x. This is the x-axis, 8 plus 4, 12. So your y in here, okay, so it is equal to 0. And then we now have your z is also equal to 0. So your z is also equal to 0. Coordinates of points B. So the coordinates of point B, so your x in here is equal to 8. And then your y in here, that is your point B, so is below the origin, and that is therefore equal to -3. And then your z of point B is equal to 0. Okay, so walang nakaparallel sa z-axis. Let's try to get the coordinate of point C. So the coordinate of point C, x is 0, y is -9. This is below again the origin, -9. And then your z is equal to 0. So we now have the coordinates of point D. So the coordinates of point D is equal to, is your x is 0, then your y in here is also equal to 0, and then your z in here is, your z is positive 6. So it's going forward. Now, so first, let us try to introduce a position vector in the direction of boom A, B, C. Now, at this time, first, let us try to introduce, okay, a position vector Okay, so that is now your R, B, C. So BC is now your position vector. Now, so that the position vector RBC is equal to xi plus yj plus zk. So this is now a position vector. Okay, from D to C. And this is now your RBC. It's a position vector RBC. So first, let's try to get the components of the distance BC. So we have the x component of the distance BC, and this is equal to B going to C. 0 minus 8 is negative 8. And then we have the y component of the distance BC is negative 9 minus and negative 9 minus and minus 3 is negative 6. So we have negative 6, and we now have to determine the z component. So the z component BC is 0 minus 0, and that one is now equal to 0. Hence, the position vector RBC is now equal to minus 8i minus 6j. Minus 8i minus 6j. So that the distance BC, so let's try to determine the magnitude of, you try to determine now the magnitude of RBC. This is therefore equal to the square root of x squared plus y squared plus z squared. So it's now equal to the square root of r squared, x squared plus y squared plus z squared. So minus h squared, so that is positive. If you square it, will become positive. H squared plus negative 6 squared, it will become positive. So we have plus 6 squared. And therefore, your RBC is now equal to, so RBC is now equal to, okay, the distance BC, or the magnitude of the position vector RBC, is now equal to h squared plus 6 squared. And this one is equal to, so this is therefore equal to 10. Hence, the unit vector in the direction of BC. So let's try to get the unit vector BC. NBC. So the unit vector NBC is now equal to the position vector BC. So that is minus 8I minus 6J all over the magnitude of this position vector, which is equal to 10. We now have the component. So we now have the component of the force F, which is equal to 850 pounds, is now equal to, so that is F ABC is equal to the vector F dot a unit vector in the direction of BC. So that is dot a unit vector in the direction of BC. So let us try to get now the Cartesian vector form of F, which is, or having a magnitude of 850. Okay, so let us try to write the Cartesian vector form of the 8 of your F directed from B to D. So, is equal to the magnitude of that vector, multiply this one by a unit vector in the direction of F. And that unit vector in the direction of F is now a position vector from in that direction all over the magnitude of that position vector. Now, if you try to go back, the coordinates of B and D are 8, minus 3 and 0, and 0, 0, and positive 6 respectively. Now, the x component, 0 minus 8 is negative 8. The y component, 0 minus and minus 3 is positive 3. And the z component is 6 minus 0, so that is equal to 6. Hence, the position vector is now equal to minus 8I plus 3j plus 6k. Let us now determine the magnitude of this position vector. So the magnitude of RBD, so that is now your D, okay. The magnitude of RBD is therefore equal to, that is now your RBD, that is equal to the square root of, we have x squared, which is 8 squared, plus y squared, that is 3 squared, plus z squared, that is 6 squared. So that one is 6 squared. And this is therefore equal to the square root of 109. 109. So the unit vector. So we now have the unit vector. The unit vector BD is now equal to minus 8I plus 3j plus 6k all over the square root of 109. So the component of the vector F along A, B, C. So let's try to determine first the vector F. So this is your vector F is now equal to 850. So that is equal to, so the magnitude of the vector F, your vector F is now equal to a vector f, multiply this one by a unit vector. So the unit vector BD is 3j plus 6k all over the square root of 109. Now, we are required to determine the magnitude of this vector, which is now your f in there. So how are we going to determine the magnitude of this vector? We know the component of this vector in the direction of ABC. So at that time, we did consider a position vector BC. So the component of this vector. So let's try to determine now the component of F along boom A, B, C. So the component of that vector along boom A, B, C is now equal to this vector dot a unit vector B, C. So dot a unit vector BC. So we have now your F ABC is now equal to the magnitude of that vector minus 8i plus 3j plus 6k, divide this one by the square root of 109 dot a unit vector. Okay, divide this one by the square root of 10. So that a unit vector BC. And the unit vector BC is equal to minus 8i minus 6j all over 10. Now, the component of this vector in the direction of ABC is 850 pounds. And this is therefore equal to the magnitude of that vector. So we have 8 times 8. So we have positive 64. And then J, 3, we do not have J in here, so 3 times 0, 0. And then we have 6 by negative 6 by negative. So there is 3j and we have minus 6j. So 3 times a negative 6 is negative 18. So 6 ang k natin. We do not have k in here. So it is equal to 0 all over 10 the square root of 109. So that the magnitude of the vector f is now equal to 850, multiply this by 10, the square root of 109, divide this one by 64 minus 18. And this is therefore equal to 1929.1929.187 pounds. So this is the magnitude of the vector f in the direction of BD. Or we can solve this one by introducing another position vector. Since because we are required to determine the component of this vector f in the direction A, B, C. Okay, before we did consider a position vector BC. At this time, let us try to consider a position vector AC. Since AC is still along ABC. So that is a position vector RAC. It's a position vector RAC. Now, so at this time, the component of the vector F from B to D is now equal to the vector itself dot a unit vector RAC. So your unit vector AC is now the position vector AC all over the magnitude of this vector. So we now have the position vector RAC is now equal to xi, again, plus yj plus zk. So components of the distance AC. So we have your x component, we have your y component, we have your z component. So these are the coordinates of A, B, C, and D. So that is AC. So it is directed from A to C. So we have Z minus A. So 0 minus 12, negative 12. And then minus 9 and 0, negative 9. And then we have 0 minus 0. So that is equal to 0. So your RAC is now equal to minus 12i minus 9j. So the distance magnitude of, so let's try to determine the magnitude of RAC. Okay, so the magnitude of RAC, so your D is now equal to the square root. The magnitude of RAC is equal to the square root of 12 square plus 9 square, or that one is equal to 15. Then the unit vector AC is now equal to minus 12i minus 9j all over 15. So all over 15. Now before your F, the vector F is equal to, so vector F is now the magnitude of this vector. So we have minus 8i plus 3k plus 6k all over the square root of 109. So we have again, from this equation again, we now have the component of the vector F along ABC is equal to 850 pounds. And that is equal to the magnitude of that is equal to that vector. So we have minus 8i plus 3j plus 3j plus 6k over the square root of 109 dot a unit vector AC. And this is minus 12i minus 9j all over 15. All over 15. So we now have 850 is now equal to F. So we have 8 multiply this one by 12. So your 8 multiply this one by 12, minus and minus is positive 96. So again, that is J. So 3 multiply this one by minus 9 is equal to minus 27. So divide this one by 15, the square root of 109. Hence, the magnitude of that vector is 850 times 15, the square root of 109 all over 96 minus 27. And this will still be equal to 1929.187 pounds. Okay, now, since AB is still along the direction of the component, so at this time, if I am going to introduce a position vector from point A to point B, hence, the component of the vector F in the direction ABC is now equal to that vector, multiply this one by a unit vector AB. And that unit vector AB is now equal to the position vector RAB all over the magnitude of that position vector AB. So again, your RAB is now equal to, so we have XI plus YJ plus ZK. So let's try to determine the components of RAB. Components of the distance AB. So that is from A to B. So we have 8 minus 12. So we have your X component, we have your Y component, and we have your Z component. So your X in here is AB, so it's directed from A to B. So 8 minus 12 is negative 4. So we have minus 3 and 0 is negative 3, and then 0 and 0, so that is therefore equal to 0. We have to determine now the magnitude. So the magnitude of RAB. So the magnitude of RAB is now equal to the square root of 4 squared plus 3 squared. And this is therefore equal to 5. So we know now the unit vector NAB is now equal to RAB, so that is equal to. So your RAB in here is now equal to minus 4I, okay, minus 3J. So minus 4I minus 3J all over 5. So let us try to determine now the from this equation again, your component of the vector in the direction ABC is 850. And your F in here is now the magnitude of F, vector F, multiplied, okay, minus 8I plus 3J plus 6K all over the square root of 109. So in the previous position vectors that we get, this is your vector F, that a unit vector AB minus 4I minus 3J all over 5. And therefore, 850 is now equal to F. So we have minus 8 minus 4 is positive 32, and then that is minus 9. So we do not have k again, all over 5 the square root of 109. So in this case, your f, the magnitude of the vector f, is now equal to 850 multiply this by 5, the square root of 109 all over 32 minus 9. And that one is now equal to 1929.187 pounds. So that is therefore the magnitude of the vector f directed from B to D. So you try to take note in here now that if you are getting the components of a vector in any desired direction, okay, if that desired direction has more than 2 points are given, so you can make use of all of this. The value of the answer will still remain the same. We now have sample problem number 5. The force FAB, 800 newtons, acts along cable AB. So we have, this is therefore the magnitude of the vector F along AB. And this is equal to 800 newtons. Determine the projected component of the force along cable AC. So what is the projected component of this force along cable AC? Express the result as a Cartesian vector. So first, let us try to determine the coordinates of the different points. So we have the coordinates of point A. So the x is equal to 0. This is the x-axis. This is the y-axis. And that is your z-axis. And then the coordinate, y-coordinate is equal to positive 4. And your z-coordinate is equal to 0. So for point B, the x-coordinate is negative 1.5. So that is negative 1.5. So your y in here is equal to 0. And then your z in here is, so this is your z, positive 1. And then at point C, the x-coordinate is positive 1.5. Now, the y-coordinate in here is equal to 0. And the z-coordinate is equal to 3. That is your z-coordinate, which is equal to 3. So we're required to determine the projected component of the force along cable AC. So if you try to take a look in here now, so the component of that vector along AC is now equal to the vector dot a unit vector AC. So that is the desired direction where the component of that vector is required. So let us try to determine first the vector directed from point A to point B having a scalar value of, or the magnitude of which is equal to 800 newtons in its Cartesian vector form. Okay, so let's try to determine the force F in Cartesian vector form. So this is therefore equal to F. Is therefore equal to the magnitude of F. Multiply this one by a unit vector A, B. So that is the direction of the force F. So first, let us try to determine now your NAB is equal to a position vector and the magnitude of AB. So let's try to determine the components of the distance AB. So the components of the distance AB, X component, we now have your Y component and your Z component. So your X in here from A to B, minus 1.5 minus 0, negative 1.5. 0 minus 4, minus 4, and 1 minus 0 is 1. Hence, the distance AB, okay, so we now have your RAB. So we now have your RAB is now equal to negative 1.5I minus 4J plus K. And therefore, the magnitude of RAB is now equal to the square root of 1.5 square plus 4 square plus 1 square, or this is equal to the square root of 19.25. Square root of 19.25. So the vector F, therefore, is now equal to the magnitude of that vector, which is equal to 800 newtons. Multiply this one by a unit vector, and that is RAB is minus 1.5I minus 4J plus K. Let's try to divide this one by the magnitude of the position vector, which is equal to the square root of 19.25. Square root of 19.25. And therefore, your F in here, the vector F, is now equal to 800 times 1.5 all over the square root of 19.25 is negative 273.505I. And then we have 800 times negative 4 all over the square root of 19.25 is minus 729.348J. 800 times 1 all over the square root of 19.25 is plus 182.3377K. So that is now the Cartesian vector form of the 800 Newton force. Since we are required to determine the component of force along cable AC, so let us try to determine, okay, a unit vector which is NAC, so that we can determine the component of the vector F in the direction AC. which is equal to the unit vector, is equal to that unit, the vector itself, dot a unit vector AC. So first, let's try to determine NAC. So we have RAC all over the magnitude of AC. Let's try to determine now your components of the distance AC. So we have your X, we have your Y, and we now have your Z. So AC, 1.5 minus 0, that is positive 1.5. 0 minus 4, so we have negative 4. 3 minus 0, so we have positive 3. So that your RAC is now equal to Xi, 1.5 I minus 4J plus 3K. So that the magnitude RAC is now equal to the square root of 1.5 square plus 4 square plus 3 square. So this is therefore equal to 5.22. So it's 5.22. Now, let us try to determine now the component of the vector F in the direction AC. Now, the unit vector AC therefore is now the position vector all over its magnitude AC, 1.5I minus 4J plus 3K all over 5.22. All over 5.22. So, let's try to determine now the component FAC. So, your FAC is now equal to the vector F, and that vector F is minus 273.505I minus 729.348J plus 182.337K. Okay, so we have that a unit vector AC, and that a unit vector AC. And this unit vector AC therefore is 1.5 over 5.22 is 0.278I minus 4 over 5.22, 0.766J, 3 over 5.22 plus 0.575K. So that a unit vector AC, which is 0.278I minus 0.766J plus 0.575K. That is that a unit vector. So that your FAC, so your FAC is now equal to, so we have minus 273.505, okay, by 0.278. And then we have minus 729.38 by negative 0.766 plus 182.337 by 0.575. So the component of the vector in the direction AB along AC is now equal to 585.028 newtons. So 0.028 newtons. So let us try to express this one in as a Cartesian vector. So express as, okay, the component of the vector directed from A to B, whose magnitude is 800 newtons, in the direction AC is 585.028 newtons. So let us try to express this component in as a Cartesian vector. As a Cartesian vector. So if you try to express this one as a Cartesian vector, then your FAC is now equal to your FAC. Multiply this one by a unit vector AC. So multiply this one by a unit vector AC. So your FAC therefore is now equal to 585.028 newtons. Okay, multiply this one by a unit vector NAC, which is this one, 0.278I minus 0.766J plus 0.575 of K. So this is therefore equal to 585.028 by 0.278 is 162.638 I. 585.028 by negative 0.766 is minus 488.131 J. And then plus 585.028 by 0.575. So that is 336.391 K. So this is the Cartesian vector form of the components of the vector AB along AC.